Something terrible is happening to China's space station.
Tiangong, once a symbol of calm, controlled progress, is now facing a problem no one fully understands. Strange signal, unexpected warnings, and unexplained changes around the station have raised questions scientists are struggling to answer. What exactly is unfolding up there? Why are officials so cautious in their statements? And how did a routine mission suddenly turn into a situation that feels far from routine? As the world watches from below, one thing is becoming clear. Something about Tiangong isn't right, and the truth may be more troubling than anyone imagined. The first sign of trouble. Shenzhou 20 was never expected to attract unusual attention. The mission launched on 24 April 2025, carrying Commander Chen Dong and crewmates Chen Zhongrui and Wang Ji to the Tiangong space station. It was part of China's standard rotation cycle, the same structure repeated across earlier flights: support scientific work, manage station maintenance, and return to Earth after 6 months. For most of the mission, that plan held steady. Docked spacecraft play 2 roles on Tiangong. They bring crews up, and they stand by as each crew's way home if anything goes wrong. Because of that dual purpose, the condition of the return capsule is monitored routinely. Window surfaces, thermal layers, and pressure boundaries are checked through a mix of onboard observation and ground analysis. These checks rarely reveal anything unusual. The system is designed to keep operations predictable. In the days leading up to the planned 5th of November return, engineers conducted the usual pre-departure review. It was during this phase that something small but out of place appeared in the imagery from the return capsule's viewport. A faint mark, difficult to interpret at first glance, but distinct enough that it didn't match previous records. At this stage, the observation was not treated as an emergency, but as an irregularity that required clarity. Window surfaces can show minor variations after months in orbit, so the team compared the latest images with earlier inspection data. The mark remained visible under magnification, and its shape differed from the patterns typically associated with thermal stress or surface residue. That was enough to pause the routine process. When an unexpected feature appears on a pressure-bearing surface, the next step is to verify its nature, not assume it's harmless. The first indication of trouble had presented itself. Not a failure, not a confirmed hazard, but a reason to slow down and take a closer look at a component that cannot be taken lightly during a crewed return. The first clue. Once engineers identified the irregular mark on the viewport, the next task was to determine what could have created it. In low Earth orbit, there are very few natural explanations for a surface disturbance on a spacecraft window. The environment around Tiangong contains a mix of operational satellites, abandoned hardware, and a growing population of tiny fragments left behind by previous missions. Most of these objects are too small to track, but they move fast enough to leave noticeable effects when they make contact with a spacecraft. As analysts reviewed the imagery from Shenzhou 20, the shape and spread of the mark became important. It didn't follow the patterns associated with internal stress, which usually creates smoother or more uniform discolorations. Instead, this feature showed a defined point with faint lines extending outward. That structure closely aligns with what engineers expect from a small object striking a hard surface at orbital velocity. This kind of assessment is not new. Space agencies regularly examine impact marks on station modules, solar arrays, and external shields. Even the International Space Station has reported similar incidents, including visible marks on its cupola windows. These cases help create a reference library of what debris-related signatures look like, and the similarities with the Shenzhou 20 window stood out quickly. The timing of the impact was harder to determine. Shenzhou 20 had been docked for months, so the contact could have occurred at almost any point during its stay. Small debris strikes do not trigger noticeable vibrations or alarms. They are silent events that leave behind only physical evidence. This makes the identification process reliant on routine imagery review rather than direct detection. What mattered was not when the strike occurred, but what it meant for the spacecraft's return capability. Even a tiny fragment if it hits at high speed, can compromise a surface that plays a role in maintaining pressure integrity. With the direction of the investigation shifting toward an external impact, the discussion moved to the next question. How could this specific type of damage affect the vehicle's readiness for re-entry? Assessing the structural risk. With evidence pointing toward an external impact, the focus shifted to understanding what the damage meant for Shenzhou 20's ability to return safely. A return capsule is designed to tolerate extreme conditions during descent, rapid heating, aerodynamic loading, and a steep change in internal pressure. Every component involved in sealing the cabin, whether a hatch, a panel, or a window, needs to remain predictable under those stresses. Even small defects can behave differently the moment the capsule begins its re-entry profile. The viewport on Shenzhou 20 is not just an observation window. It forms part of the capsule's pressure boundary, meaning its material needs to perform consistently to prevent pressure loss under increasing thermal gradients. Microfractures disrupt that consistency. While the cracks identified on the viewport were small, their structure raised questions about how far the stress might travel once re-entry begins. To evaluate this, engineers conducted a standard structural review. They compared the fracture lines with known behaviors of similar materials under load, reviewed past cases of window anomalies in other programs, and examined the possible interaction with surrounding thermal layers. The assessment didn't show an immediate risk while the spacecraft remained docked, but the data also didn't provide the level of certainty required to confirm that the window would tolerate its full descent profile. Human spaceflight standards rely on clear thresholds. If a component cannot be confirmed as stable through every stage of re-entry, the vehicle is not cleared for use. In this case, the fracture introduced enough uncertainty that Shenzhou 20 could not meet that benchmark. The conclusion was straightforward. The spacecraft was no longer suitable for a crewed descent, even though the damage appeared small. Once that determination was made, the mission's priorities had to change. The return plan now needed a different approach, reconfiguring the mission. After Shenzhou 20 was deemed unsuitable for re-entry, the next challenge was operational. The crew still needed to return to Earth, and the station required a safe evacuation option at all times. Fortunately, the timing of the incident coincided with the arrival of Shenzhou 21, which had just completed its docking sequence to deliver the next rotation crew. Under normal circumstances, the incoming spacecraft becomes the next crew's emergency return vehicle. This time, it had to assume a different role. Mission planners began evaluating whether Shenzhou 21 could support an early return for the outgoing crew. The spacecraft was fully functional, recently arrived, and had passed its own inspection checks. Using it for the Shenzhou 20 crew's descent was feasible, but it created a new complication. The newly arrived Shenzhou 21 crew would have no return vehicle of their own once Shenzhou 21 undocked. Despite that issue, the priority was clear. A functioning, certified capsule existed on the station, and it had to be allocated to the crew whose vehicle could no longer be used. Preparations were made for the transfer, focusing on stability, resource planning, and crew procedures. The shift was not routine, but it followed established principles. When one return capsule becomes unavailable, the next viable option takes its place. The Shenzhou 20 crew completed their handover duties and boarded Shenzhou 21 for descent. Their return on the 14th of November 2025 confirmed that the replacement vehicle functioned as intended. However, their departure left a noticeable gap in station operations. For the first time in China's space station program, the new crew remained on board without a dedicated escape craft. That situation introduced a different type of risk, one no longer tied to the damaged window, but to the station's immediate emergency capability. A station left without a return option. With Shenzhou 21 used to bring the previous crew home, the Tiangong station found itself in an uncommon situation. 3 astronauts in orbit without an active return vehicle docked. This scenario is rare in modern human spaceflight because the return capsule is not only the way home at the end of a mission, it is also the primary escape option if anything unexpected occurs on the station. Fires, depressurization events, cooling system failures, or even a collision threat all require a fully functioning spacecraft ready for immediate use. For the Shenzhou 21 crew, this gap did not pose an immediate danger, but it did change the operational landscape. Every system on the station, including life support, electrical distribution, and thermal control, continued functioning normally. However, station planners must always account for scenarios where rapid evacuation becomes necessary. Without a capsule attached, the crew's margin of safety is reduced. In practical terms, this means that the on-orbit schedule becomes more conservative. Maintenance activities are reviewed with more caution, and certain operations that involve changing the station's configuration may be paused until a replacement vehicle arrives. This type of vulnerability is not unique to Tiangong. The International Space Station has experienced similar periods when a Soyuz or Starliner vehicle was unavailable, requiring adjustments in day-to-day planning. The parallel serves as a reminder that even well-established programs encounter situations where contingencies must be put in place. For Tiangong, the absence of a return vehicle was less a crisis and more a temporary window where procedures needed to adapt. The China Manned Space Agency acknowledged the situation publicly, explaining that the damaged Shenzhou 20 capsule would remain in orbit for now, and that the next mission, Shenzhou 22, would be prepared to restore normal operations. Until then, the crew would continue working with heightened attention to system stability. The station remained fully functional, but the priority shifted to minimizing any activities that might introduce unnecessary risk while awaiting the arrival of the next spacecraft. Contextualizing the incident. To understand the broader implications of the Shenzhou 20 damage, it's important to view the incident within the larger environment of low Earth orbit. The region surrounding Tiangong has become increasingly crowded. It now contains thousands of active satellites and a far greater number of inactive ones, along with fragments produced by collisions, rocket upper stage breakups, and decades of accumulated space activity. Many of these objects are tracked, but millions of smaller particles, some no larger than a grain of sand, move through orbit undetected. These fragments travel at speeds that make even minor contact significant. At roughly 28,000 kilometers per hour, a particle too small to see can strike with enough force to damage external panels, sensors, or, as in Shenzhou 20's case, a Windows surface. This is not an isolated risk. The International Space Station has reported several similar impacts over the years, including visible chipping on its cupola windows and damage to radiator panels. Other spacecraft, including commercial vehicles, have documented comparable encounters. The Shenzhou 20 incident fits into a pattern that experts have been warning about for years. As more countries and private organizations operate in orbit, the density of objects increases. Each addition raises the probability of collision, particularly with smaller fragments that cannot be predicted or avoided. Agencies use debris tracking systems and maneuvering strategies, but these tools primarily address larger objects. The micro-debris that likely caused the Shenzhou 20 fracture remains one of the most difficult threats to mitigate. The situation has renewed discussion around debris management and long-term sustainability in orbit. Cleanup technologies, active removal missions, and improved shielding have all been proposed, but implementation takes time. For now, spacecraft operating in low Earth orbit must accept a level of exposure to debris impacts that cannot be fully eliminated. The Shenzhou 20 case stands as another example of how a small, untracked fragment can influence major mission decisions and reshape standard operations. It's the available evidence. Several aspects of the incident remain unclear. These uncertainties do not point toward a larger mystery, but they represent gaps that engineers must account for when determining the future handling of the Shenzhou 20 capsule. The first unknown is the exact moment the impact occurred. Shenzhou 20 remained docked to Tiangong for more than 6 months, and during that time, the station completed thousands of orbits. Any one of those passes could have been when the fragment made contact. Because micro-debris collisions do not generate sound or detectable vibration, they are rarely noticed in real time. A second unknown involves the extent of secondary stress around the damaged area. The visible fractures indicate the initial point of impact, but engineers must also consider how force travels through layered materials. Spacecraft windows involve multiple coatings and structural layers, and a strike that penetrates one may create stress patterns in the others. Some of these effects do not present themselves until detailed post-flight analysis, meaning the full behavior of the material under re-entry conditions cannot be confidently modeled while the spacecraft remains in orbit. Another open question is whether the debris caused any additional, non-visible changes elsewhere on the capsule. Most spacecraft rely on thermal blankets, micro-meteoroid shields, and structural layers that can absorb or mask small impacts. If a fragment contacted the window, it is possible, though not confirmed, that other areas experienced minor contact during the same time frame. Without physical access to the spacecraft on Earth, engineers must rely on imagery and sensor data, both of which have limitations. These uncertainties do not imply undisclosed damage or unexpected failures, but they do reinforce why Shenzhou 20 cannot be used as a return vehicle. Re-entry tolerances require absolute clarity, not a best estimate or an acceptable risk range. Until the capsule can be examined directly after controlled deorbit, these unanswered questions remain part of the overall assessment. For planners, that means shifting attention away from attempting to salvage the vehicle's role and toward preparing the next mission that will restore normal station operations. Preparing Shenzhou 22. With Shenzhou 20 unavailable and Shenzhou 21 already used for the previous crew's return, the responsibility for restoring full capability on Tiangong now falls to Shenzhou 22. Under standard conditions, each Shenzhou mission follows a predictable preparation timeline, including months of system checks, integration procedures, and coordination with the Long March launch vehicle. The debris incident did not cause a crisis, but it did introduce urgency into a process built around careful scheduling. When the China Manned Space Agency confirmed the damage on Shenzhou 20, they also stated that Shenzhou 22 would launch at an appropriate time. In practice, that means preparations would be evaluated based on the spacecraft's readiness rather than its original position on the calendar. The mission must satisfy every technical requirement, but planners now weigh that against the need to restore a docked return vehicle to the station as soon as practical. Accelerating a human spaceflight mission involves more than moving up a launch date. It requires verifying the spacecraft's environmental systems, checking the docking hardware, ensuring all subsystems meet certification standards, and coordinating flight windows with Tiangong's orbit. Even under compressed timelines, no step can be omitted. This approach ensures that the next capsule sent to the station is fully capable of supporting an emergency return scenario from the moment it arrives. There is also the question of whether Shenzhou 22 will launch with a crew or arrive as an uncrewed vehicle. An uncrewed flight would simplify certain aspects of mission management, while a crewed launch would allow the next rotation to continue as originally planned. Both options remain viable, and the agency's decision will reflect the balance between operational needs and long-term planning. What is certain is that Shenzhou 22 now carries additional responsibility. Its arrival will restore standard safety margins, allow the station to return to its usual operational rhythm, and close the temporary vulnerability that emerged after the Shenzhou 20 window damage. Until then, Tiangong remains fully functional, but with stricter operational boundaries and a stronger emphasis on risk control. Long-term adjustments ahead. The Shenzhou 20 incident has prompted a broader review of how China approaches risk management for its space station operations. While the event did not create an emergency, it highlighted areas where procedures may need refinement as the orbital environment becomes more demanding. One of the most immediate lessons involves the value of redundancy. Tiangong typically maintains access to a return capsule at all time, but the debris strike revealed how quickly that system can shift when a single vehicle is compromised. Future planning may include tighter inspection intervals, additional imaging protocols, or new guidelines for assessing return capsule readiness earlier in the mission cycle. More advanced onboard diagnostics could also be introduced to detect small changes in structural components. Although windows are inspected regularly, the availability of higher resolution or more frequent analysis would help identify anomalies sooner, allowing teams to evaluate risk with greater confidence. Another area under review is the shielding configuration around sensitive components. Current materials provide reliable protection against many types of microdebris, but the impact on Shenzhou 20 demonstrates the limits of how much protection a window can receive. While major redesigns are unlikely in the immediate future, incremental improvements, such as modifying external covers, enhancing protective coatings, or adjusting docking orientations, may help reduce exposure to undetectable fragments. Operationally, the incident reinforces a principle already familiar across international space programs. Not every threat can be tracked, and not every risk can be removed. The key is to create systems that respond effectively when the unexpected occurs. In this case, the mission team executed the required adjustments efficiently, but their experience now becomes part of a larger knowledge base that will influence how Tiangong missions are planned going forward. Shenzhou 22 will restore full operational capability, but the impact of the Shenzhou 20 damage extends beyond a single spacecraft. It introduces considerations that will shape future procedure, vehicle preparation, and station safety strategy for years to come. The future of human spaceflight. The damage to Shenzhou 20 and the subsequent mission adjustments reflect a challenge facing every nation operating in low Earth orbit. As more spacecraft, satellites, and debris populate this region, the risk environment continues to evolve. Human spaceflight has always depended on precision and reliability, but today it must also account for external conditions that cannot be fully controlled. The Shenzhou 20 incident demonstrates how a single, untracked fragment can influence mission planning, crew logistics, and operational decision-making on a large scale. For China's Tiangong program, the event marks an important moment in its operational history. It is the first time a crewed Shenzhou spacecraft has been withdrawn from service due to confirmed structural concerns while docked. The response, reassigning the return vehicle, adjusting on-station procedures, and preparing Shenzhou 22 with added urgency, illustrates both the robustness of the existing system and the areas where flexibility is essential. In the broader context, this incident aligns with challenges already seen in other programs. The International Space Station has dealt with coolant leaks, microfractures, and window impacts. NASA, Roscosmos, and other agencies have each faced situations where hardware behaved unexpectedly due to debris or aging components. These parallels highlight a shared reality. Maintaining long-duration human presence in orbit requires constant adaptation and an understanding that the conditions outside the spacecraft evolve as rapidly as the technology within it. Looking ahead, the focus is likely to shift toward improving debris monitoring, enhancing spacecraft resilience, and developing new strategies for managing risk in congested orbits. Active debris removal, upgraded shielding technologies, and more diversified evacuation options are all part of ongoing discussions within the space community. The Shenzhou 20 case will now join those discussions as a recent and relevant example of why these efforts matter. Despite the unexpected challenges, Tiangong remains stable, its systems performing as intended, and its crew continuing their mission with the support of ground team. When Shenzhou 22 arrives, the station will regain its full operational margins. Until then, the Shenzhou 20 incident stands as a reminder that human spaceflight, even with decades of experience behind it, still depends on constant vigilance in an environment where the smallest objects can have the greatest impact. That's it for today. Let us know your thoughts in the comments down below. Don't forget to like and subscribe for more space content.